So as we've said, for any reaction, at some point we can reach a point where the rate of the forward reaction, which is our reactants going to products, that the rate of that forward reaction is equal to the rate of the reverse reaction, the products going back to reactants. And what we mean by that is that, at least in theory, every reaction is reversible. That the starting materials can react to form products, and the products can react to reform the starting materials. And that is a situation that we define as chemical equilibrium. Now, this doesn't mean the reaction has stopped. The concentrations are not changing anymore, but that's because, again, we have an equal rate of forward versus reverse. Now, just because we say that every reaction is theoretically reversible doesn't mean that it's something we can always see. For example, the reaction of hydrogen gas plus oxygen gas to form water, as written here, is in theory reversible. But if we wanted to be realistic about the way we wrote this reaction, we should probably write it more like this. Where that arrow indicates the forward reaction, and this arrow indicates the reverse reaction. If you can't see that arrow for the reverse reaction, that's fine, because that gives you an idea of how small it is. Now, while we haven't defined the concept of an equilibrium constant yet, the equilibrium constant for this reaction is 2.4 times 10 to the 47th. And just to give you an idea of what that truly means, if we have a reaction where the equilibrium constant is over 1,000 or over 10,000, then we already say that that's a reaction that pretty much only goes toward the product side. And given that this one is 2.4 times 10 raised to the 47th, that means this reaction goes basically only in one direction. Again, it's theoretically reversible, and we'll talk about what this number here means later on. But again, this one is really, in theory, only going to go in one direction. All right, so let's look at some simpler reactions. So we have this reaction, dinitrogen tetroxide can react to form two molecules of nitrogen monoxide. And we have a rate, and therefore a rate law, for the forward reaction, and therefore a rate constant. We'll call that K1. Now, we haven't gotten into rate laws in this class, and it's not something that we're really going to do in this course, but let's just, basically that constant K1 is something that relates to how the reaction works. There's also the same thing for the reverse reaction. We'll call its rate K minus 1. So we can define a rate law for the forward reaction and a rate law for the reverse reaction. So really all these rate laws mean, because again, this isn't something we're going into in this course, but these rate laws are a way to express how quickly the reaction occurs, and they're based on the concentrations of the reagents. So for the forward reaction, we can say that the rate, or I'm sorry, this isn't something we can just say, this is actually something you have to determine experimentally. So for the forward reaction, the rate is found to be equal to K1, which is its rate constant. Again, that's a value that's determined experimentally. And that's times the concentration of N2O4. For the reverse reaction, we use the other rate constant, the K minus 1. And it's found for this reaction that the rate of the reverse reaction is equal to K minus 1 times the concentration of NO2 squared. Now remember what we said equilibrium is, though. We said that equilibrium is when the rate of the forward reaction is equal to the rate of the reverse reaction. And so at equilibrium, for this reaction, K1 times the concentration of N2O4 is equal to K minus 1 times the concentration of NO2 squared. And so we're going to sort of redistribute this expression. We're going to put the constants on one side and put the reagents on the other side. So we get K1 over K minus 1 is equal to the concentration of NO2 squared over the concentration of N2O4. And this expression is what we define as the equilibrium constant. So now, we don't want to have to go through that series of steps every time, because that turns out it's something you can only do experimentally. So we have to go through, and is there a generic way to determine an equilibrium constant? So for any generic reaction, and what these are, the lowercase letters are your stoichiometric coefficients, whereas the capital letters are our reagents in these reactions. So the equilibrium constant, KEQ, although sometimes we abbreviate this instead as KC, is equal to the concentration of each of the products. And we raise the concentration of each of the products to their stoichiometric coefficients. So we take the concentration of C, which is one of our products, raised to its coefficient. We multiply that by the concentration of the other product raised to its coefficient. In the denominator, we do the same thing, but for the starting materials. So each of their concentrations raised to their stoichiometric coefficients. And so as long as we know a balanced equation for the reaction we're looking at, we can use this generic type of formula to come up with the equilibrium expression for any reaction. So let's do one. So here's H2 plus I2 gives us 2 hydrogen iodide, and it's already balanced, so I'm going to save you the trouble of doing that. So all we need to do here is take our equilibrium constant, and again, in the numerator go our products, the denominator are our starting materials. So what are our products here? Well, our product is HI. That's our only product. What power do we need to raise that to? Well, we need to raise it to its stoichiometric coefficient, which here is 2. In the denominator, we need the starting materials. So our starting materials are hydrogen and iodine. So we need each of their concentrations in the denominator. Now, what coefficients do we need? Well, each of these doesn't have a coefficient, which means we know the coefficient is 1. So each of these would be raised to the first power, which of course that's not something that we normally draw in. So that would be our equilibrium expression. So let's ask the following question. So for the reaction we just talked about, H2 plus I2 forms HI. What we have here is the number of moles of H2 and the moles of I2, and we say they're placed into a reactor and we get an amount of product. So what's KEQ? So the way that we typically do a problem like this So we already know what the equilibrium expression is. We found that a few minutes ago in our previous problem. So in order to be able to calculate the equilibrium constant, what we need are values for concentrations of hydrogen, iodine, and HI when we're at equilibrium. And so the way that we normally do that is by setting up something that we refer to often as an ICE table. And an ICE table, this stands for initial, change, and equilibrium. Now remember, these are concentrations, not numbers of moles. But in this question, the difference doesn't really matter. Why doesn't it matter? Well, because we're in a 1 liter reactor. And so if you're calculating molarity based on 1 mole of volume, then moles and molarity are going to be equal to each other. So our initial number of moles of hydrogen and iodine, as well as their molarities, is 0.1. How much HI did we start with? We start with none. Now we ended with 0.158 of the HI. So how much did it change by? It went up by 0.158. Now where did that 0.158 come from? Well, it had to come from the starting materials. So they had to decrease. But they don't decrease by 0.158. Why? Well, because the stoichiometry is 1 to 2. So they would decrease by half of 0.158. And we would have 0.021 left over at equilibrium. So now we can calculate our equilibrium for this reaction. KEQ is equal to our concentration of the product squared over our concentrations of the starting materials. And we get 56.6. And you can see our units here will all cancel out, and that's typical for equilibrium expressions, is they end up being unitless.